in the next couple of minutes is just emphasize the need to understand aerosols and their contribution to pollution. So firstly, what is an aerosol? Well, in general terms, when we talk about aerosols, what we are talking about are solid or liquid particles dispersed and suspended within a gas. And aerosols are key to our understanding of the most important global challenges, including disease transmission, including COVID-19, air pollution and public health, climate change, and therapeutics and drug delivery. And so to address these global challenges, we must collaborate across disciplines and institutions to better understand particle properties and their effects. The work of my group spans across particle synthesis, characterization and measurement techniques, understanding particle dynamics, and the effects of particles and those on climate change and air pollution. In terms of particle synthesis, we generate particles for our experiments in the lab. We look at particles produced from combustion engines and from road transport and aviation. We're looking at characterizing the chemical composition of particles produced from peat burning and biomass burning. And we're also developing techniques to understand the charge state on aerosols, which is important if you want to manipulate the particles with electric fields. We're incorporating our understanding of dynamics into models, so here with computational fluid dynamics, and then we're also really interested in the effects that these particles have once they're released into the environment. And I'm going to talk a little bit more about a case study where we're looking at the effect that soot particles emitted from aircraft engines have an effect on contrails, these line-shaped clouds you see following the aircraft. And you can see them and observe them for yourself in the sky. So the formation of contrails is to a large extent controlled by the number of soot particles that are emitted from aircraft engines. And so a detailed understanding of the number and the properties of those particles is required to understand the following properties of the contrail. And what we've been able to do is simulate the emissions from all flights taking place over Japan, and we can do this for other airspaces, and therefore simulate the contrail that was produced from a particular flight and then its effect on climate change. So contrails have a warming effect because they trap outgoing long-wave radiation, but they can also have a cooling effect because they can reflect sunlight back out to space. And it's the balance of those warming effects and cooling effects that determines whether a contrail has a overall net warming or net cooling. And also the lifetime of the contrail is really important to understand because that determines the magnitude of that effect. So with our work, because we were able to identify and simulate in detail each individual flight, what we were able to show is that only 2% of flights contribute the vast majority of contrail warming effect. And what that means is that we can radically change the way we think about avoiding contrails formation and reducing the climate impacts of aviation. So we only have to deal with these 2% of flights rather than deal with all of flights that take place. And we can think about just minor changes to altitude, flight altitudes, that would have a really significant effect on those contrails. And so we're working on pushing this idea forward and thinking about how we can get this implemented, at least in a trial. So we're really interested to hear from you. We've got facilities for characterization of aerosols and opportunities for engagement with industry to co-sponsor and co-supervise PhD projects through our Centre for Doctoral Training in Aerosol Science.